my name is Florian Fischer, and I recently did my bachelor thesis here at the Electronic Visions Group in Heidelberg, and also Ben Größ is doing his bachelor thesis here right now, and I'm going to talk a bit about the things we did and what we are still working on. So here in the group, we are interested in mixed signal neuromorphic hardware systems with analog neurons and synapses. So, and these systems are intrinsically event-based and also continuous in time. So to accommodate this and also potentially have further efficiency gains, we're working on an event-based training framework for SNNs, which is called Jackson. So Jackson is a Python library building upon JAX, and it supports event-driven SNN processing for inference and also gradient computation. So the main difference with respect to many other libraries is that it uses event steps instead of relying on a time-gridded approach. So the processing directly jumps from one event to the next one, and this also allows for a higher temporal resolution and potentially a better scaling for sparse networks. And the backward pass is also done in event-based fashion, so where event prop can be used. So we wanted to extend Jackson to arbitrary topologies, and so that we also have recurrent feedback connections. And to achieve this, all layers are evolved to the next state at each iteration. And also a minimum delay between recurrent connections is introduced to guarantee a forward direction in time for the processing. And you can see on the right that for a given layer, we start with its state and then always have to find the next event, which can either be an input event or an internal event, meaning that one of the neurons of the layer spikes. And the times of these internal events can be found by using either analytical formulas or numerical root finding or spike data, which we gain from a hardware run. And then it has to be checked if the event can be used or that the layer can be evolved to that point in time, and ensuring that no input spike can arrive before that time. And then the layer can be evolved to that point in time using the dynamics, and also the discrete transition can be applied. And then we arrive at the next state. And so for the backward pass, we used event probe with an extension for constant delays. And we also implemented for feed-forward networks in Jackson event-based learning of synaptic delays, which is based on the extended event prop method, which was developed by Balázs Mészáros. And so the neuromorphic intermediate representation implements an exchange format for topologies of spiky neural networks. And we propose an extension to NEAR for data exchange between different neuromorphic platforms. And we aim for, or the aim behind this is that we can do in-the-loop training for example, on hardware systems with software frameworks that are not inherently connected. So for this, we introduce a NEAR data class, which both supports event-based and time-gridded data. And so for our example, we trained the yin-yang data set on using the BrainScale's true system for the inference and the Jackson library for the gradient computation. And so the NEAR data exchange is then used for the in-the-loop handling. So basically Jackson or our hardware backend could be replaced by other neuromorphic platforms or frameworks that support the NEAR data exchange. And so in the future, we want to evaluate the performance of our event-driven training methods and also optimize them further. And also we want to implement gradient estimation and networks with local plasticity rules. And finally, we also we would like to do event-based training of more complex neuronal morphologies. So thank you a lot for your attention.